Okay, so hello everyone, welcome again. Today we have Gonzalo Villa, who is a PhD student in Cambridge. He's doing his PhD with Fernando Quevedo, and he will give two lectures on the standard model. And over to Gonzalo.
Okay, thanks, Ahmed. Hello, everyone. Thanks for staying until the end in the lectures. Uh, I'm very, very happy to be able to have this chance of telling you about the standard model, about you know, the most interesting or our most fundamental, experimentally assessed understanding of nature. Uh, Yes, I would like to begin first by thanking, of course, Ahmed and Nabil and also ICTP because I think this initiative is very nice and it's very important, and I hope you are enjoying it and learning a lot of physics. And and so what is the goal? So let's get started. The goal is to describe the standard model. Now, what is the standard model? This is a relativistic gauge quantum field theory featuring scalars, fermions, and gauge vectors, so vector fields. In three different phases. We have the Coulomb phase, which is realized, for instance, in electromagnetism. We have the Higgs phase, also known as spontaneous symmetry breaking. And we have the confined phase, which is how quantum chromodynamics behaves at low energies. Today we're going to focus on the phenomenon of spontaneous symmetry breaking. If you have any questions, raise your hand in the chat, and yeah, I guess I will stop as soon as possible. If I don't see the chat, Ahmed, feel free to interrupt me. Okay, so let's get started. Now, notice everything. What is SSB? Thank you. Very good point. This is spontaneous symmetry breaking, which is the topic of today. And QCD is quantum chromodynamics, which we'll talk a little bit about in the next lecture. Okay, very good. So, notice everything I've said here is about symmetries. Relativistic talks about the space-time symmetries of the theory. Gauge theory is, features internal local symmetries, as we will see. And the fact that, fields behave like scalars, fermions, or vectors is also a statement regarding the transformations or the behavior under the action of symmetries. Similarly, the Coulomb and the Higgs phase are statements about whether symmetries are realized in a vacuum or not. And we will, and this is what we're going to talk about today. So symmetries are very important in quantum field theory. But in order to build some intuition, I would like to talk about quantum mechanics instead. So let's start building by the building blocks. So let's talk about quantum mechanics. We know the game. In quantum mechanics, one has a Hamiltonian. So consider a system described by a Hamiltonian H on a Hilbert space H tilde, sorry, curly H. The unitary operator U implements a symmetry if, well, I should have said U maps states in the Hilbert space to the Hilbert space, and unitary means that the inverse of U is the same as its adjoint. Now this operator implements a symmetry if it commutes with a Hamiltonian. Okay. You can check because U is unitary. This is the same as H commuted with U equals 0. Now, what are the questions? QCD at low energies, does it mean low temperature or non-relativistic? Very good. I could be studying QCD at 0 temperature and nonetheless study its high energy regime if I'm colliding sufficiently energetic particles. And non-relativistic, QCD is a relativistic theory. In that its components are not massive. Its fundamental components, quark and gluons, until the Higgs mechanism kicks in, but we'll talk about that later. But yes, don't worry too much about QCD today. We'll talk about it more on Monday. Okay, so back to the quantum mechanical systems. Why is this useful? So why is understanding symmetries of the system useful? Well, we have the generate states, and we can understand why. So consider two states. Psi1 and Psi2, which are elements of the Hilbert space, related by a symmetry transformation which means Psi2 equals U acting on Psi1. So I have Psi1, I acted on it with U, and it maps to Psi2. Then it follows that Psi1 and Psi2 have the same energy. That is, they are degenerate. To see this, let H psi1 be E1 times psi1, H psi2 equals E2 times psi2. That is, the states have energies E1 and E2. Then I can write E2 acting on psi2 as H acting on psi2. Now, because this is a symmetry, U implements a symmetry, this is the same as this quantity here. And this by assumption is U times psi1. This is identity because U is unitary. So this is U acting on H acting on psi1, which equals E1 U psi1 E1 psi2. The equality therefore holds for non-trivial psi2 if E1 equals E2, which completes the proof. The states are therefore degenerate. States related by asymmetry transformation are degenerate. They have the same energy. What else? Well, there are selection rules in the theory. That is, because U commutes with H, we can choose a basis that diagonalizes both operators. So U acting on psi is little U acting on psi, H on psi equals E on psi. And then we claim that time evolution from an eigenstate of U cannot map two states with different eigenvalues of U. This is easy to prove. Consider quantum mechanics in Schrödinger picture. We have the Schrödinger equation in units h bar equals 1. If psi is an eigenstate, this is easy to solve. And in general, this is a solution. And now if U acting on the initial state gives me little U on the initial state, then U acting on psi of t will give me the same thing. To see this, just use the above equation. and not u commutes with the Hamiltonian. So we can commute it with through the exponential as well to see that just Taylor expand and commute u. And in the end, we get u acting on psi of t. From which it follows that matrix elements as matrix elements, I should have said, involving states with different u eigenvalue are forbidden by symmetry. And this is a selection rule. There are transitions which cannot occur. There are transitions among states that cannot occur. Oops. Note, and if I have time on Monday, I will tell you a little bit more about this. This implies that small breaking of symmetries due to new physics allows for such transitions with small probability. Observing such transitions is in the standard model a signal of new physics. For instance, proton decay. I hope I will have time on Monday to tell you about this story about proton decay because it is very, very interesting. But for today matters, all we want to know is about this selection rule. Okay, and our last one, the last one in quantum mechanics. Oh, is there a mathematical principle to explain spontaneous symmetry breaking? Yes, this is the idea. We will talk, in the rest of the lecture, we will cover what is spontaneous symmetry breaking and how it manifests itself in a standard model. Okay, so last one in quantum mechanics. Why this is interesting? Why is having symmetries in quantum mechanics is interesting? Because in addition, there are conservation laws, which is quite related to the above. We say that asymmetry is continuous if the operator u of theta can be written as, if the operator u can be written as Let me erase that. Sorry. If so, then Q is Hermitian, is an operator, and therefore a quantum mechanical observable. Note that if U commutes with H, then Q also commutes with H. As you can see by expanding the exponential and imposing the commutation relation. So the eigenvalues of Q are also conserved under time evolution. But these ones are observable. So this is a conserved quantity. Okay, this is all I have to say about quantum mechanics. We have...
Gonzalo, you have some questions in the chat.
Oh, thank you. What do I mean? Very good. What do I mean by small breaking of asymmetry? Small breaking of asymmetry imagine I have a Hamiltonian H equals H0, which has some symmetry, let's say about parity, to be concrete. Symmetric under parity. That is, I take the vector x and map it to minus x. And then I add another interaction, lambda times h breaking. And this is not symmetric under parity with lambda much smaller than 1. Then what we say is that, well, this is an explicit breaking, not spontaneous breaking. We will see what spontaneous means later. This is a spontaneous break, an explicit breaking, sorry, of the symmetry. And if lambda is small, which I have assumed, we do perturbation theory. Perturbation theory. And then if I have two states, so that is diagonalize H, diagonalize H0, and treat H int perturbatively. But if I diagonalize H0, then I have my Hilbert space is broken into two pieces, states that are even under parity and states that are odd under parity. So consider plus, minus, states even or odd under parity respectively. Then a transition from minus to plus is different than zero because the Hamiltonian H breaking, yes, sorry, wrong notation. I meant H breaking perturbatively. Then this matrix element here would be zero if there was no HB. But then, because of the breaking of the symmetry, this will be different than zero and order lambda. Now, if lambda is very small, which I am assuming, then the probability of this transition is order lambda squared. And if I do n experiments, I have a very small probability lambda squared of this happening. And I could in principle measure lambda. So measure the breaking of the symmetry by looking at these transitions, which are not allowed in the free Hamiltonian. I hope that is clear. Do you have any more questions on that? Okay, so this is order lambda because lambda breaks the symmetry explicitly. Okay, I hope that was clear. Now, what happens in free theory? So this was overview, really. If you want to learn more, you can go to any standard textbook. I recommend Weinberg's quantum mechanics book. Okay, so let's move on and see what happens in field theory. So in order to make contact with the standard quantum mechanical discussion that we just covered, I'm going to use the framework of canonical quantization, which is what you've been doing throughout the course, except in Nabil's lectures, which were introduced path integral quantization. But the canonical quantization makes the connection to quantum mechanics simpler, so I want to start there. So consider canonical quantization. So what is this? What is what we do in canonical quantization? We quantize, and this is something that might not have been emphasized a lot in the previous lectures, and it's very important for symmetry breaking. What we quantize are fluctuations of fields with respect to a given background. typically space-time independent, so as to be compatible with Lorentz invariance in the so we quantize in the interaction picture and the resulting Fock space describing the physics is, if you want, a product of ordinary Hilbert spaces of the simple harmonic oscillator. So, the free field system is a bunch, if you want, of simple harmonic oscillators. Many simple harmonic oscillators, quote unquote. So what is a symmetry in a field theory? This is a transformation on fields. If it's on fields, it's an internal transformation, an internal symmetry. And or space-time coordinates which we called external that leave the action invariant. And this union. Can you say more about space-time independent background? Yes, I maybe let's wait until the first example, and if you want in the first example, you can ask me again, because I will go back to it. But it's essentially, when I say space-time independent, I'm just saying that I'm gonna have a field configuration that looks so I'm going to study this field configuration for which the vacuum expectation value of phi is not a function of space-time coordinates, and these are the fluctuations to quantize. This is what I mean by the background being space-time independent. So, it's constant everywhere. In principle, this need not happen. This vacuum expectation value of phi only needs to solve the equations of motion. But then you have a price to pay. You're gonna break Lorentz invariance, and funny things will happen. And this is not what we want to do today, although it is possible to do. If you want to learn about these kind of things, I strongly recommend this book here. It's a book of Cliff Burgess on effective field theories. I'm gonna write down the name. because quantum field theory has many applications apart from particle physics. But today we want to do particle physics. I hope that was clear. Okay, now back to the symmetries. Let us consider an internal symmetry. In general, this is a transformation that maps an operator phi or a field phi to another field phi tilde by the operator action of the operator action u. And now we would like to recover the standard formalism we were applying in quantum mechanics. Recall that in canonical quantization, what I do is use interaction picture, then the fields, the free fields satisfy the equations of motion, and when I quantize, then pi is a linear combination of A and A dagger, an integral, a Fourier transform, and so on. But this is this is the important part because these are the operators in the game. Now, if this is the case, then A tilde, which is hopefully obvious notation for the creation operators of this guy, the annihilation operators of that guy, must be equal to U acting on AK acting on U dagger. And we're almost there. I can define the following state. I state K tilde by the action of A tilde plus on the vacuum. And then, if the state K defined as AK on 0 satisfies that K equals K tilde U equals U acting on K, then the discussion above applies. The above, and when I say above, I mean quantum mechanics. The above quantum mechanics discussion applies. And the question is, oh, sorry. Okay. When is that true? Well, we have K tilde by definition equals A tilde on 0. And we saw before that, again, by definition, this is what happens. And the question is whether U acting on K equals this quantity. Well, the equality is true if and only if U acting on the vacuum maps to the vacuum. And we say then that the symmetry is manifest. Otherwise, the symmetry is spontaneously broken. Oh. Okay, so okay, so this was very obscure, I would say, very formal. But I need to develop a little bit more of formality, and then we will use an example to illustrate all of this, and you will see it will become more clear. Okay, so the statement U with 0 different than the vacuum is or we will define as the condition of spontaneous symmetry breaking. But this is not the most useful way to look at things, at least for our current purposes. And why is this true? Because when you had been discussing symmetries in quantum field theory before, you study transformations of the following form. Phi goes to e to the I alpha a t a on phi, which is not of that form. Sorry, this is not true. So let's make contact with this formulation. So the goal of the next 5 minutes is to make contact or make a statement about spontaneous symmetry breaking in terms of the generators TA. The generators of well, to do so, note that if I take let me call this 1 and let me call this 2, if I equate 1 to 2 and expand to first order, writing u equals e to the I, what? I want to say q. Let me call it QA. You will find that the commutator of phi and q equals the action of the generator of phi. Equation 3. Now take the vacuum expectation value of this to find that 0 acting on TA phi, which I'm gonna call just TA phi, equals 0 phi q minus q phi. I have forgotten, yes, I forgot to say something. Note the spontaneous symmetry breaking condition in terms of Q is Q acting on 0 equals 0. So Q annihilates a vacuum. Again, to see this, just remember that U acting on 0 equals I to the IQ acting on 0. Taylor expands, and symmetry breaking is that, is that this is different than 0. If Q annihilates a vacuum, the symmetry is manifest. And using this observation in here, we find our useful condition for spontaneous symmetry breaking. Is that the vacuum expectation value of TA acting on phi is different than 0. Because if the symmetry was manifest, this Q annihilates 0, and this Q annihilates 0, therefore this must be 0. Okay, and this is what we are going to take as the condition for spontaneous symmetry break. So let's, before having a quick break, well, are there any questions of this? Or maybe I do the example and things will become clearer. But yeah, if there are any burning questions, please ask. Okay, good. So let's study an example. The global U1 system. Let's write our favorite Lagrangian minus a half d mu phi star d mu phi minus lambda over 4 pi bar phi minus v squared squared. where lambda is positive, V is real, and phi is a complex scalar. We know oh, why U on null state means symmetry. Symmetry, not something else. I'm not sure I understand the question. Can you rephrase it? Yes. So if U acting on the null state, which is this expression here, gives the null state, then this is the null state, and this is therefore true. So then K tilde and K are related by asymmetry transformations as states in the Hilbert space, and then all the discussion I had described before applies. I have described in the context of quantum mechanics. I guess you need to check that you commute with the Hamiltonian, but if it leaves the action invariant, it will. No problem. So, the idea is that if U acting on zero is not zero, then this does not apply. The standard discussion in quantum mechanics does not apply, and we want to understand what is the physics, what happens when U does not map to the vacuum. Okay. So as we know, I think from the first class or something, this theory has a global U1. For which I map phi to E to the I alpha phi, and alpha is real. And again, this is of the form I was saying before, phi goes to the exponential of something times phi. Unlike phi goes to some U times phi times U dagger. So as we will see, or as we want to show, the symmetry is spontaneously broken broken if V is different as. So how can we say this? Well, remember, first we have to identify the background. Which is the same as identifying the vacuum of the theory. Well, the vacuum must solve the equations of motion, which in this case is the Klein-Gordon equation. Which will be something like, which is something that goes like 5/5 minus v squared. A homogeneous static solution. This is a background. Satisfy box phi bar equals 0. So mod phi squared must equal v squared. Okay. And that is our background. Now we have to study the fluctuations around this background and quantize them. So consider the fluctuations. So let me write phi as phi vacuum excitation value plus delta phi, which I'm going to write in this way. Where phi 1 and phi 2 are the fluctuations to quantize. Now, this is not really the best way to parameterize the fluctuations, but I think it illustrates better the physics, so I'm going to use it. But in the example of the U1 gauge breaking, I will choose another parameterization. Now, what we want to do is to derive the Lagrangian for the fluctuations. We have to evaluate the different terms. So for instance, d mu phi is 1 over root 2, d mu phi 1 plus I 1 over root 2, d mu phi 2, phi star phi equals, you know, it's phi over phi minus v squared. I have it here. 2v phi 1 over square root 2 plus v squared over 2 phi 1 squared plus phi 2 squared. I hope that is correct. And so the Lagrangian can be divided into a kinetic part and an interaction part, which read as follows. The kinetic part is minus 1 over 2 d mu phi 1 d mu phi 1 minus 1 over 2 d mu phi 2 d mu phi 2 minus lambda v squared over 2 phi 1 squared. So we have a massless and a massive scalars. Real scalars. And then they are coupled, and there is some interaction Lagrangian, which I am not going to write because I didn't write before, but you can work it out. It's easy, consider it an exercise. And you will see there are interaction terms among phi 1 and phi 2. Now, what happens? If V equals 0, the symmetry is manifest. And the states are degenerate. If V is different than 0, there is spontaneous symmetry breaking and the degeneracy is lifted. To see this, to see that the symmetry is broken, recall our definition or our useful way to parameterize spontaneous symmetry breaking. It was TA acting on phi on the vacuum equal this different than 0. Well, TA is defined by phi goes to e to the I alpha A TA acting on phi. Now, in our case, e to the I alpha A TA is just e to the I alpha TA equals 1. And then the question is whether phi, the vacuum expectation value of phi equals 0. But we have seen that it is phi. By solving for the background equations of motion. And I think this is equation 4. So for V different than 0, indeed, there is spontaneous symmetry breaking. And as we can observe, a degeneracy has been lifted. Which was one of the consequences of the quantum mechanical analysis, if you remember. So as we see, spontaneous symmetry breaking has consequences, and the typical quantum mechanical discussion does no longer hold. So the usual QM description or intuition doesn't hold. Does this mean that the spontaneously broken symmetries are not important? The answer is no. It's absolutely no. We have Goldstone's theorem, for instance. Any system with spontaneous breaking of a continuous global symmetry has a massless state, which is called Goldstone boson. And in our U1 case was what we called phi 2. So there was a massive phi 1 and a massless phi 2. And the fact that there is a massless field holds in general for any continuous global symmetry. You are invited in the exercises to prove this theorem. So this is an exercise. Okay, so I think this is a good moment to take a short break. Are there any questions?
I'll pause the recording.
Okay. Can you please explain this answer a bit more? So, the answer about the symmetry breaking. Yes, so, if you have a massive field, imagine I have a massive field. Then if I'm working at low energies, if I collide particles at energies much smaller than the mass of this field, I will never be able to excite it. So it will be hidden in what we call the ultraviolet. Whereas if there is a massless field, it will always be interacting at low energies. So it will make an appearance. And this is a physical implication of the breaking of the global symmetry, that it manifests itself at low energies as a massless field with a particular set of interactions, which you are invited to explore in the exercise. And again, I should refer to the book on effective field theories of Cliff Burgess for much more discussion and applications in many systems. No problem. Okay, so we have studied how how global symmetries break. Now let's study how gauge symmetries break. So let me start by the end. I will tell you the results. Spontaneous breaking of gauge symmetries leads to the Higgs mechanism. Which is a key ingredient in the standard model. So let's start now by the beginning. Consider the simplest system I can think of, the abelian Higgs model, which describes superconductivity, I believe. What we have is a Lagrangian with the field strength of a vector field, the kinetic term, no 1/2, the kinetic term of a complex scalar, and the same symmetry breaking potential as before. Here we have F mu nu, the covariant derivative. Let me see what sign I chose. This sign, A mu, and my favorite scale, which is the same one as before. As you know from previous lectures, this system enjoys an E1 gauge symmetry. For which infinitesimally phi goes to phi plus I alpha phi, and A mu goes to A mu minus 1 over E d mu alpha. I should have said E is real. It's actually positive. It's a coupling constant. Now we're going to do something that is going to prove very, very, very important. And we're going to count degrees of freedom. Strictly speaking, you have to do this when V equals 0 and quantize the fluctuations and so on. We have one massless vector field, which remember is 2 degrees of freedom, is the transverse oscillations, only the transverse oscillations are physical. And we have one complex scalar, which has real and imaginary part and therefore 2 degrees of freedom as well. So this adds up to 4 degrees of freedom. Sorry, I should have said this is the degree of freedom. Now, I'm going to make you a spoiler of what is going to happen. If spontaneous breaking of the symmetry happens, then we're going to still have 4 degrees of freedom, but the interpretation is going to be much different. In particular, we're going to get a massive vector field, which has 3 degrees of freedom because the longitudinal part can now be excited, and a real scalar field, which is called the Higgs field. So in the following 10 minutes or so, we're going to describe this physics. Now we have to do, as usual, first identify the background. So as we know, we must have phi squared equals v squared, because this is the same as before. And now quantize the fluctuations. If you remember before, I chose phi equals phi1 plus phi2, and they were orthogonal directions in field space. But that is not really the best way to think of the physics. We would like to make the physics more manifest. Now remember, I just told you that the potential looks like this in field space. And that was terrible. So we're going to divide the fluctuations. We are going to parameterize a radial fluctuation and an angular fluctuation. That is, I'm going to write phi as v plus eta of x over the square root of 2 e to the I psi of x over square root of v, where I have chosen numerical constants so that I get the right kinetic terms and so on. Otherwise, I could always redefine the fields. Okay, now this makes a symmetry manifest. The symmetry transformation only acts on this guy, and you can check in the global U1 system, this would be the Gaussian boson, this theta here. So this is an exercise for you, although it will not appear in the list because it's kind of quick, it's very fast. But the symmetry transformation only acts on psi and on theta, and that theta would be the Goldstone boson in the global U1 system. Now to work out, we want to work out the Lagrangian of the fluctuations. So we have to take the derivatives and so on. We have to do things like this. D mu phi equals d mu eta root 2 v plus eta of x over root 2. Of course, I am not deriving this. I had a note, but you can derive it yourselves. It's not difficult. So we're gonna get the right kinetic term for eta, and this funny term here and the potential has just a bunch of self-interactions for ah. Okay, now notice the important part is that theta, aka the Goldstone boson candidate, only appears combined with a mu. In the combination and so can be gauged away a fact that I strongly recommend you to try and check. Oops. So I'm gonna call all of this combination a mu. And this is called the unitary gauge. In this gauge, the Lagrangian reads again a kinetic term or quadratic term and an interaction term, where the kinetic term equals the kinetic term of the scalar, the kinetic term of the vector, a mass term for the scalar, and interestingly, a mass term for the vector. I will talk about this a little bit more. Let me just give you the interaction Lagrangian for completeness. If I worked it out, but do check it, this is what the interactions look like. And you could work out the Feynman diagrams and so on from these interactions. Now, this is the theory of a real scalar coupled to a massive vector field with no gauge symmetries. At least with no obvious symmetries. So again, degrees of freedom, 3 from the massive vector, plus 1 of the real scalar, add up to 4 as before. So we have the same number of degrees of freedom, they have been just shuffled around. And this is the Higgs mechanism. Upon spontaneous breaking of a gauge symmetry, there would be Goldstone boson becomes the longitudinal component of the gauge effect. Which is the usual statement that the vector field eats up the Goldstone boson. Okay. Are there any questions at this point? Well, let me emphasize something and then we can ask questions. Notes. Happened in a given gauge. But the physics is gauge invariant. this gauge is just useful to identify degrees of freedom but the computations can be done in a gauge. And when I say computations, I mean S matrix element and so on, so observables. If you don't believe me, check the Goldstone equivalence theorem. For it's done in the book of Beskin and Schroeder. Chapter 21, I believe. Okay, now are there any questions before we move to the last part of the lecture? Okay, so in this last part, I want to cover the same thing just with a non-abelian symmetry. So in the last lecture or 2 lectures ago, Nabil taught you what a group is or gave you the idea of what a group is and how Yang-Mills theory, so the theory of gauge symmetries, can be generalized to objects that do not commute, vector fields that do not commute among each other. So we would like to understand how this happens, how the Higgs mechanism works in the non-abelian case. And now the idea is that non-abelian groups have several generators and symmetries can be partially broken to subgroups of the original symmetry group. And we're going to do an example of this. What a subgroup is a group which is contained in a larger group. A simple example, rotations along the z axis form a group because I can add them up, subtract them, and so on. And they belong to the subset, and they are a subset of all the rotations in three-dimensional space. This group is called SO2. And these guys are a subgroup of rotations in 3 dimensions. Which is called SO3. In the language we've developed, if the transformation is generated by a bunch of TAs, that is phi goes to this combination, or noting that if if the group is on higher dimensions, then phi looks like a vector. It's a bunch of scalars really in components and infinitesimally. Sorry, lower index. I want to do lower index. Phi is going to transform in this way. Okay. For instance, in the example we will see, phi is going to be a three-dimensional vector, and these guys here are going to be the generators of rotations among the different axes. Then the subgroup generated by TA. Remember, these guys are called the generators of the group, these TAs. So that TA acting on phi equals 0 is preserved. Again, this was very, what do you call it? Dark, probably. So let's illustrate an example. Right. Which is the example I was telling you about. I break SO3 to SO2. The Lagrangian is again my favorite Lagrangian. Nabil has told you the story about non-abelian groups. Now we have a trace, we have a covariant derivative. I am adjoining now because these guys are vectors. So this is the straightforward generalization of what we were doing before. Now, phi is a vector with phi 1, phi 2, and phi 3 is a triplet of real scalars, and the generators of the rotation group Pi in matrix notation minus I, where this is the Levi-Civita symbol, the totally antisymmetric symbol. If you don't know what this is, don't worry, I'm going to show you what the matrices look like in 1 second. Okay, but just in case you don't remember, the different objects in the Lagrangian are now a non-abelian field strength, which looks in this way. So it has an additional self-interaction term. Where f, a, b, c are the structure constants of the group. And when I write f mu nu, this is if you want a vector, and these are the basis vectors, which are the generators of the group, of the representation. And again, I have a covariant derivative, which acting on the individual components acting this way. So let's play the same game as before. Degree of freedom counting. Well, first we have to recall the defining representation of SO3, which is the one we're using today. This doesn't matter, but it's just for completeness. Has 3 generators, which are the generators of angular momentum. So they are rotations along each axis. What this implies is that there are 3 massless vector fields and therefore 6 degrees of freedom. And in addition, there is a triplet of real scalars. So there are 3 real scalars which add up to give 9 degrees of freedom. And again, this will be mixed upon spontaneous symmetry breaking. Now, there is a spontaneous symmetry breaking. The background satisfies phi star dot phi equals V, where now the dot is a product, is a vector product. And without loss of generality, I can write my scalar potential. Sorry, my scalar field. Not, I've chosen this way to parameterize the fluctuations because it is easier for me. I could have, of course, just say, call this phi1 in this direction, phi2 in this direction, and phi3 in this direction. But that is much less useful and hides the physics. So this is a right, or this is a more appropriate choice of coordinates if you want. But of course, I have 3 degrees of freedom, and it doesn't matter how I choose to parameterize them. Now the idea is that I can perform a gauge transformation here. This is exactly the same story as before, just with more matrices and looks more complicated, but it's exactly the same. I can choose again unitary gauge, so that this is what my field and fluctuations look like. I am absorbing the fluctuations in a gauge transformation, which will eventually become the longitudinal component of the vectors. I'm just going to focus on the kinetic part of the Lagrangian. You can work out the interaction one. And I have the standard kinetic terms for the fields, and you can work it out, consider it an exercise. A mass term for these 2 guys. So these features a massive real scalar, i.e. a Higgs field, two massive vectors, A1 and A2, and a massless vector A3. I guess upper index. So this counts degrees of freedom 1 from the real scalar, plus 3 from a massive vector, plus 3 from another massive vector, plus 2 from the massless vector equals 9. So everything checks as before. It is the same amount of degrees of freedom, just shuffled around. Now, because there is a massless vector, this suggests that the symmetry is only partially broken. And we would like to check. So let's check. In order to check, remember, I have to ask whether this is 0 or non-zero. And then along the A direction, the symmetry will be broken or not. Remember, the TAs are just the generators of angular momentum. The ordinary ones in quantum mechanics. So T1 on phi is what we call typically Lx or H bar Lx or so on, which is just this matrix. So it leaves the x-axis invariant and rotates around in the other two directions. Now this is different than 0. So the symmetry is broken along the one direction. Let's see what happens for T2. This is what in quantum mechanics we call Ly. This should be something like this. So it leaves the y-axis invariant. And again is non-zero. So the symmetry is also broken along T2. What about along L3? This should leave the z-axis invariant. So I hope this is the generator. And surprise, surprise, this is 0. So there is a remaining SO2 symmetry. Which is the one that is generated by the remaining massless field. Okay, I know this was fast, but I wanted to illustrate the example. This concludes the class. I think I'm right in time, hopefully.
Well, turn off the video.